Hello everybody, welcome to today's lecture on continuing the review for material balances. We had performed material balance calculations and we have reviewed the concepts using one example for chemical reactions. Today we will review the fundamentals associated with the biochemical reactions using one example problem which covers all the aspects of biochemical reactions with respect to cell culture, and we will also talk about recycle as part of this problem. Let us go to this example problem. Pichia pastoris is a methylotrophic yeast that has classically been used as a cost effective eukaryotic expression system. The R&D division of Genentech has developed a new strain of Pichia pastoris that has the capability of producing bevacizumab, a monoclonal antibody that is used as an anti-cancer drug. They are setting up a new production plant in India to produce this drug using the engineered Pichia pastoris. You are hired by this production plant of Genentech. The first project assigned to you is to design a chemostat that can be used to grow this new strain of Pichia. Based on the data obtained from the R&D division, you know that the growth follows Monod's model. Your team manager has asked you to design a chemostat that can handle 100 liters per hour of sterile feed with glycerol as the substrate with a concentration of 40 grams per liter. Calculate the volume of the chemostat if the final biomass concentration has to be 20 grams per liter. Draw the flow sheet before solving the problem. While you are working on the design, you learn that a cell separator that can separate the cells from the exit stream broth can be purchased for 5 lakh rupees. In an effort to impress your manager, you also design a second setup where a fraction of the Pichia pastoris is recycled using this cell separator. Based on the specifications of the cell separator, you know that the recycle ratio has to be 1.5 and the concentration of the cells in the recycle stream will be twice the concentration of the cells in the exit stream. If the same feed as in the first design is to be used as fresh feed, what does the volume of this chemostat have to be to obtain the same biomass concentration in the exit stream? Again, draw the flow sheet before solving the problem. If the cost associated with building a new chemostat is rupees 10,000 per liter, what will be the savings for the company if the filter is installed and the cells are recycled? Note that the actual bioreactors that will be installed will have volumes that are multiples of 50. Data given is mu m equals 0.18 hour inverse, Ks is 0.5 grams per liter and y-axis is 0.55 grams per gram. So, you can assume that the dissolved components do not affect the densities. Now that all the information is available to you in the problem, let us first start with drawing the flow sheet. For the first system, it is quite simple. You have a single standalone chemostat with a sterile feed and one exit which would contain the biomass and unutilized substrate. However, for the second setup, you would have a reactor and a cell separator with a recycle stream. Let us see how these flow charts would look, and we will try to label all the streams so that we can perform these calculations. For the first setup, you have a chemostat. So, this is the representation for a chemostat, has one input and one output. The input is fresh feed which is coming in at a rate of F equals 100 liters per hour. We have also been told that it is a sterile field, which means x naught equals 0 grams per liter, and substrate concentration in this stream has been given as 40 grams per liter. The substrate used here would be glycerol. So, let us assume that the cells are growing inside the reactor with a specific growth rate of mu, which follows Monod's model, and the volume of the reactor would be V. So, you have an exit stream. For steady state conditions, the exit flow rate would also be F, which is equal to 100 liters per hour, and we have been told that the desirable biomass concentration would be 20 grams per liter. We also know there will be some unutilized substrate which is glycerol leaving the system. However, we do not know the concentration of this substrate. Now that we have drawn the flow sheet for the first setup, let us try to draw the flow sheet for the second setup. For the second setup, you have the chemostat. In addition to this, you also have a cell separator from which the recycle stream is sent back to the fresh feed. So, we have a fresh feed. So, we have been told that this fresh feed has the same properties as the fresh feed of the previous setup. So, we know that F here would be 100 liters per hour and this is a sterile fresh feed. So, x naught equals 0 grams per liter and substrate concentration would be 40 grams per liter. You have an exit stream which is taken to the cell separator and the desired products are taken out. You also have a recycle stream which is sent back to be mixed with the fresh feed to form the total feed. So, this recycle stream, we have some information about this. We know that the recycle ratio is equal to 1.5. So, as we know that the fresh feed is coming in at a volumetric flow rate of 100 liters per hour, we can assume that the recycle would be 1.5 times F, which is based on the recycle ratio. So, this recycle stream is flowing in at a rate of 150 liters per hour. We have also been told that the biomass concentration in the recycle stream is twice that of the biomass concentration in the final exit stream. So, this would be 2x and this would also have some unreacted substrate accompanying the recycle stream. So, your final exit stream, we know that would have to have a flow rate of F which equals 100 liters per hour, so that you can maintain steady state. The biomass concentration has been given as 20 grams per liter and this would also have an unreacted substrate which is at a concentration of S, which we need to calculate. Because we now know the value for x, we can calculate the biomass concentration in the recycle stream as 40 grams per liter. So, this stream which leaves the chemostat and enters into the cell separator would have a flow rate of F plus R and it would have a biomass concentration of x1 and a dissolved substrate concentration of S. Now that we have all the information regarding both the systems, let us try to solve this problem using the fundamentals we had learnt for biochemical processes. For the setup 1, let us write a biomass balance. Input minus output plus generation minus consumption equals accumulation. At steady state, we do not have any accumulation. We also do not have any consumption, assuming that there is no cell death. So, we are only left with generation, input and output. So, input term would be f x naught, which goes to 0 because x naught is 0 in the sterile feed. You have f x as your output and generation, if you remember, is given as mu x v, where mu is the specific growth rate, x is the biomass concentration in the exit stream, thereby the biomass concentration inside the reactor also, v is the volume of the reactor, this equals 0. So, from this we know that mu v equals f, which equals 100 liters per hour. So, now this can actually be substituted to your mu max S divided by K S plus S, which is the Monod's model. So, if we know the value for S, we can calculate mu. Once we have the value for mu, we will be able to calculate the volume of the reactor. For this, we need to write a substrate balance. The substrate balance would be F S naught minus F S minus mu x v divided by y x s equals 0. So, F S naught is the substrate coming in, F S is the substrate leaving and minus mu x v divided by y x s is the substrate which is being consumed. There is no generation or accumulation terms for the substrate. So, substituting the values for F S naught and mu v and also for x and y x s, we can calculate the value for S. Let us do that. So, F is 100 times S naught, which is 40, minus 100 times S minus mu times v is calculated as 100, which is F, and this times x divided by y-axis which is 0.55 equals 0. We know that the desired x is 20 grams per liter. Substituting it here to the equation, we can calculate S as 3.64 grams per liter. So, now that we have the substrate concentration, we can calculate the value for mu by substituting the value of mu max which is 0.18 times S divided by Ks which is 0.5 plus S. This gives you a value of 0.158. So, now that we have the value for mu as 0.158 our inverse, we can calculate the value for the volume as 100 divided by 0.158 which is basically F divided by mu, giving you a value of 631.9 liters. As we have been told that the chemostats are available only in the multiples of 50. So, the reactor which has to be installed would be 650 liter reactor. So, this is the volume of the reactor which is required if we do not have any recycle. Let us now consider the second part of the problem where we have to account for the recycle stream also. So, in this system we have the chemostat and the cell separator. So, for performing the balance equations for the chemostat, we need to know the biomass which is leaving the chemostat, which would be the biomass concentration inside the chemostat also. This information is required for us to calculate how much biomass is present and how much substrate would actually be leaving the system, thereby we can calculate the specific growth rate inside the chemostat. For getting the information about the biomass concentration in the stream leaving the chemostat, we have to choose the cell separator as the system for writing the balance equations. Let us take the cell separator as the system of interest. For the cell separator, let us write a balance equation for biomass. So, the biomass balance for a cell separator would be input equals output. So, input is F plus R times x1 and your output would be F times x plus R times xr. We know that the value of x is 20 grams per liter and value of xr is 40 grams per liter. We also know the values of F and R. So, substituting all of them here, we can calculate x1 as 32 grams per liter. Now that we have the information about the total product stream which is leaving the chemostat, we can start writing the balances for the chemostat itself. So, for the chemostat, we can write a biomass balance. So, the biomass balance for the chemostat would be input minus output plus generation minus consumption equals accumulation. No accumulation and consumption, we are assuming that there is no cell death. So, consumption goes to 0. So, input is you do not have any input through the fresh feed, you only have biomass input through the recycle stream. So, you have R times xr as the biomass entering through the gross feed into the chemostat. Your gross product stream contains F plus R times x1 biomass. Generation of the biomass in the chemostat would be mu times x1 times V which equals 0. So, now that we have this equation, we already know the values for R, xr, F and x1. So, we can calculate the value for mu V. So, from this equation we get mu V equals 62.5 liters per hour. So, now we have written the balances for biomass. So, next step is to write the substrate balance. So, for the substrate balance, again it is input minus output plus generation minus consumption equals accumulation. No consumption or generation for the substrate. So, you are left with only input, output and consumption. Input for substrate would come through both the fresh feed and through the recycle stream. You have F S naught through the fresh feed plus R times S in your recycle feed, and you have exit stream as F plus R times S, and you would have consumption given in terms of mu x1 V divided by y axis. So, again we are assuming that there is no other consumption of substrate other than to form the biomass. This equals 0. So, we already know the value for F S naught, R and mu times V x1 and y axis. Having all this value, we can calculate the value for S as 3.64 grams per liter. Now that we have the value for x, we can substitute it back to the Monod's model, where it is mu equals mu max S divided by Ks plus S. So, knowing the value for mu max Ks, we can calculate mu as 0.158 our inverse. So, we know mu V equals 62.5 liters per hour. So, this implies V would be 395.6 liters. So, the reactor which would be used, which would have to be purchased, would be 400 liters. For the first setup, we had calculated the reactor volume to be 650 liters, and for the second setup with recycle, we have calculated the reactor volume to be 400 liters. From these two values, we know that there is significant cost savings. So, we need to account for how much cost can be saved by using this recycle stream. So, cost saved would basically be 650 times 10,000, which is the cost for per liter reactor of a chemostat, minus 400 times 10,000. So, this is the difference in the cost for the reactor. In the cost saved, we should deduct the cost associated with the purchase of the cell separator. So, this would give us a total cost saved of 20 lakhs. So, by using this cell separator and a recycle stream, we would be able to save 20 lakh rupees just for the installation process. Obviously, there will be more savings due to the operational costs being cut down as the cells are being recycled. With this, we come to the conclusion of the review for the basic aspects of material balances. Thank you and goodbye.